We're going to use this session to look at the book's introduction to the basic commands in R. And let's just start reading. R uses functions to perform operations. So think of functions as an action or a verb, to kick, to boil. To run a function called, it is just a generic function. Think of it as a placeholder. You have to give it a name. Functions have to call a function. You need to specify which function you'd like to use. Called func name. We type func name, and then you give it your inputs or arguments. I think we're just taking two as an illustration, where the inputs or arguments, input 1 and input 2, tell R how to run the function. Do they? I think it's what the function is meant to kind of sort of evaluate, if you will. A function can have any number of inputs. For example, to create a vector of numbers, we use the function C for concatenate. This is one of the more often used functions. Any number inside the parentheses are joined together. So the following command instructs R to join together the numbers 1, 3, 2, and 5, and it will be an ordered list. So we're not going to refer to these four as a set. You may remember that there's no specific ordering in a set, but in a vector, swapping two entries in a vector changes that vector if those two entries are not equal to each other, and to save them as a vector X. So this first line is doing two things. It's creating the vector. It's a 4-element vector, and we're saving it in X. Notice the convention where you leave a space between what you're creating and what you're going to save it into, or what you're going to save it as. When between the X, the arrow, this is a single object, and in this case the vector. Now what does this one mean in parentheses? Or those are brackets, so maybe we should distinguish. The book said parentheses, that's referring to these sort of, your ordinary brackets, what you'd use when just writing any language, any natural language, any non-mathematical language. Let's go into R. And we'll do it right now. So X, this, so I'm going to define X, or I'm going to save into X, and I'll do it for entry 1, 3, 2, 5. 1, 3, 2, 5. There's no specific pattern over here, so you have to specify each entry explicitly. As soon as I run the script, two things are going to happen. Number one, the console tells you what you've just executed, or what RStudio has just compiled, and also you can now see it in your environment. This is just a really great way of keeping track of any variables that you have defined. If you want to see the full list of variables, it might be ls, and if I run it, it's now given me kind of like a vector, right? But a vector of not numerical entries. If you see the inverted commas, that means it's just text. And again, you see the one in brackets. If it's square brackets, I'll just refer to them as brackets. If I want to call R, if I want to call X, beg your pardon, I just type X. Print works as well. Print, and it's produced the same thing. Now, if this was so narrow, if this was so narrow like this, and I had to run it, although that hasn't changed much. Let me see if I run it like this. Yeah, it's still saying 1 in square brackets. I was expecting. What if it was a longer vector? What if it was a longer vector? So, what if it was like this? If you kind of have like overflow, and now I run. Do you see the 19 in brackets? So all that it's telling us is that this entry is the 19th entry. So the brackets are there to give you an idea of the position of any item that you're looking at. We'll delete all this. Let's go back to the book. Note that the arrow is not part of the command. Rather, it is printed by R to indicate, we're referring to this arrow over here, to indicate that it is ready for another command to be entered. We can also save things using equals. That works as well. You hardly ever see anyone use it, rather than, how are we even going to refer to this, rather than this arrow. Okay. Let's also create y. So y is the vector 1. Let's see. It might make more sense to put them side by side while sharing my screen, but let's see if we do it like this. So x is 162. X is the vector, and we're using equals this time around. 162. Y is the vector 143. You can add these vectors, you can multiply them. Let's run the entire code. And now notice the global environment. If we run ls as we did earlier, it's giving us 2 items. You could save that as something else. You could say my list of variables, my variables. Remember, everything is an object. So now that's saved. That's saved over here. We have 3 vectors now. We have x and y, and we have, well, I typed mu variables. We can leave it that way. It's also a vector. It's 2 entries long, but it's saying CHR. So that would probably mean characters. I don't know if that means that they are a string, probably. Hitting the up arrow multiple times will display the previous commands, which can then be edited. But this is assuming that we're working in the console. So that's if we're working in the console. If we're working in the console, you can, and we're seeing yesterday's commands, 2 days ago, 3 days ago. I prefer to work over here. I think the advantages, the pros definitely outweigh any drawbacks. This is useful since one often wishes to repeat a similar command. True, but you can just copy and paste the way I'm working. In addition, typing question mark in front of a function will always cause R to open a new help file window with additional information about the function. So when we were fitting linear models, we had the LM function, linear model, and I had done exactly that at one point. If I run this, we now see all this documentation. Usually there are links as well where if you click on them, it will take you to perhaps a repository, and there will be further details to be read in such places. We can tell R to add 2 sets of numbers together. It will then add the first number from x to the first number of y. Very, it's what you would expect. However, x and y should be the same length. Now, if they're not the same length, I don't think it produces an error. So in our calculators, you would expect an error. You may have encountered, using the Casio 991, you may have encountered, besides math error, syntax error, and stack error is when you give a kind of too much work. You may have encountered dimension error. However, R is so flexible. If I create, for example, 10, 11, and we save it. What if I do x plus z? Oh, okay, it doesn't work. It doesn't work. So in this specific case, the book isn't being overly cautious. It is in fact undefined. We can ask for the length of a vector. So I could say length of mu variables, and that's 2. It's made up of 2 entries. And as we saw just now, but this time we won't get a dimension error, we can add. You could also multiply, you could divide, and it will always compute the operation on a term-by-term basis. So if I do x division by y, what do we get? We get 1 division by 1, 6 division by 4, and 2 all over 3. The ls function allows us to look at a list of all the objects, such as data and functions, that we have saved so far. The rm function can be used to delete any that we don't want. Interesting. It is also possible to remove all objects at once. Okay, so let's have a look. Let's clear these things, but the variables are still there. So what if I do rm, and I say, let's try removing mu variables and z. And that's removed them. Now if I want to remove everything, oh, to my knowledge, there's no undo button. So now that I've removed them, you can't just press Ctrl Z. What does Ctrl Z do, in fact? It probably just takes you back to some previously typed text. It is Ctrl Z. Ctrl Z is just changing. And interestingly, at least on mine, Ctrl Y isn't working. If I want to delete everything, it is rm list, and we tell the rm function delete everything. Delete everything that's defined in the environment. And that didn't work because I only had the ls shaded. But if I shade everything, or if I leave my cursor anywhere on this line of code, pressing Ctrl Enter gives us the following message: environment is empty. The matrix function can be used to create a matrix of numbers. Before we use the matrix function, we can learn more about it. So question mark matrix. And you need to get used to the convention. So for example, how does R populate a matrix? If it's a 3x3 matrix, how is it going to fill the 9 entries? To my knowledge, the default is it moves, I think, vertically. So it fills the first column, then the second, and the third. Although you could specify that you actually want to fill row by row. Let's have a look. The help file reveals that the matrix function takes a number of inputs. And in fact, to see those inputs, if you type simply, and this is the great thing of using something like RStudio. Remember, there's R, but what we're using is, I think the acronym is an IDE. Not entirely sure what it stands for, but it must be something like, developer environment, if I had to guess. If you simply type matrix and you tab, and then you tab again once you're within the parentheses, you get exactly, you need to give it the data, you need to give it the n row, the n call, the by row, the dimension names, and that's it. These are all the functions. You don't necessarily need to specify all of them. Some will be defined by default. So if you leave the by row empty, look, in fact, it's telling you if you specify that it's false, the matrix is filled by columns, which might be contrary to what I said earlier. No, I think I was correct. Otherwise, and so that means the default. Otherwise, the matrix is filled by rows. So let's have a look. Let's have a look. So let's see. It's asking for data. It's asking for data. Let's just say 9, 8, 7, -1. So that's the first thing. Now, once you press comma, if you tab again, and normally good practice is that you leave a space. At least typically that's how I see it in, how about this textbook? Yes, there is a space, right? It doesn't change the syntax. That space makes no difference. Now it's saying n row, the desired number of rows. So we'll take 2, and call, we'll take 2 again. I'm going to leave everything else at default. And what has it done? Yes, it's as I described earlier. It took this vector. I'd like to make it entirely clear, you don't need to type the entries of the vector within this line of code. You could call this my vector. You could have my vector over here, and you've defined my vector earlier. So my vector and this, and we get the same matrix. I've kept the same matrix. I've kept the same vector, the same 4 numbers as we had in the previous example. Now, if you tell it by row false, now that means it's going to fill. It's going to do it this way. Now, actually, that's the same, isn't it? So I needed to tell it, please fill row row. So true. And now what do we get? 9, 8 are in the first row, 7, -1 are in the second row. Note that we could just as well omit typing data equals n row equals and n call equals in the matrix command above. That is, we could just type this. It is a bit dangerous. One, even just for legibility. You might struggle to remember if, in this case, it's the same number of rows and columns, but if they were unequal numbers, just in terms of auditing your code, it's not entirely clear. And number 2, you're kind of trusting that you're placing everything in the right position. So it's always a lot safer. Let's see what the book has to say about it. However, it can sometimes be useful to specify the names. I would say always be useful to specify the names of the arguments passed in, since otherwise R will assume that the function arguments are passed into the function in the same order that is given in the function's help file. So the great thing, if we just find where we were reading, is that if you're specifying the names, you don't need to follow a specific order. So you could start by row equals true. You could then say n row is 2, n call is 2, and then you only give the entries towards the very end. And we're going to get exactly the same. We're going to get exactly the same matrix as we had earlier. As this example illustrates, by default, R creates matrices by successively filling in columns. Alternatively, and this is what we used earlier, we're now filling row. Notice that in the above command, we did not assign the matrix to a value, such as x. In this case, the matrix is printed to this screen, but is not saved for future calculations. The square root function returns the square root of each element of a vector or matrix. The command x squared raises each element of x to the power of 2. Any powers are possible, including fractional or negative. You get the idea. I'm going to move on. Stop me where necessary, as always. We've been using this function quite a bit these past few sessions. How do you need to read it? R norm. Norm is a specific random variable. It's the one where I usually mention heights of individuals, IQ results. The R norm function generates a vector of random normal variables with, just put my phone on silent, with first argument n, the sample size. So going back into R, let's delete everything. Can even clear the environment by clicking on this, looks like a broom. Let's clear everything. And let's call them observations. R norm, not R unif, not R bine. These are just different. I'm listing a couple of examples of different distributions. We're going to take a normal distribution and we need to specify, number one, how many randomly generated values following this distribution do I need? Let's take 100 of them. And now I need to specify, now this is a word we haven't really used until now, the parameters. Every random variable, normal distribution, binomial, uniform, there's the Poisson, gamma, beta, Pareto, Weibull. There's an entire, maybe in a future session, I'll show you I'll show you the list of formulae and tables that the Institute and Faculty of Actuaries uses. It's the same. They will be the same ones that you will use during your exams when you eventually start writing them. Every random variable has specific parameters. So if it's a binomial, for example, either heads or tails, you could say my parameter is 50%. So that's a fair coin. But maybe you want to take heads or tails with a 40% chance of heads. So that would also be binomial, but with a different parameter. So you need to think of it as, just like in your previous studies, you had families of parabolas, families of lines, families of circles, families of ellipses. Within each family, if you take the family of lines, then each member of that family is uniquely defined by its gradient m and its y-intercept c, provided that the line is not vertical, right? If it's the family of parabolas, then each one may be defined uniquely by its quadratic, linear, and constant a, b, c coefficients. It's the same thing with random variables. You have a family of random variables, all the random variables that are normally distributed, the normal distribution. Each normal distribution is uniquely defined by its parameters. And in the case of the normal, there is the mean parameter. We usually use the Greek letter mu. Mu is letter M in the Greek alphabet. So I could take, for example, in a previous session, we took 180. Think of that as your mean height in centimeters in a specific population. And by population, that could be you're only looking at all the accountants in wherever, in Mozambique. And then the variance or standard deviation, and we normally use sigma for the standard deviation. It can't be it has to be strictly positive. If it was zero, and we discussed this last time, there is no variability. There is no variability. The higher it is, the more variability there is within the data. So let's take, for example, 20. And maybe we'll take 1,000. Maybe we'll take 1,000 of, or hey, 10,000. All right. Notice that it typically displays the first 1,000 entries. You could manually override this, although I've never done it myself. And now you could get an idea of the shape of your data by doing this. We have that histogram, and we have the mean, median, and mode. That's the great thing about normal distribution, that the mean, median, and mode all coincide. Theoretically, they all coincide. Now, in your data, since you're only looking at a sample, you're only looking at 10,000, in this case, observations, they won't necessarily coincide perfectly. In fact, we could do summary of this, and the median and the mean aren't exactly equal, but I would imagine most of us would probably describe them as close enough to be considered for all intents and purposes as equal. Notice the minimum and the maximum, 110 and 257. If I had to change the standard deviation to only 5, you're expecting the data to be more clustered, more concentrated about the mean. And this time around, that doesn't seem to have changed anything. Did I run this? Yeah, so look now. The minimum is 161 as opposed to 110, and as opposed to 257, which is humanly impossible, right? Can anyone or statistically would be a major outlier. Now the greatest data value generated is 200. The mean doesn't change, the median doesn't change. The R-norm function generates a vector of random normal variables with first argument and the sample size. Each time we call this function, this simply means, you run it. We will get a different answer unless we use set seed, mentioned 2 sessions ago. Here we create 2 correlated sets of numbers, x and y, and use the core function to compute the correlation between them. Now, we're not necessarily going to go into an exact mathematical definition. I would imagine that you've heard the phrase correlation does not imply causation. So What do we mean by all this? Let's just run it. Let's just run it. So we're going to generate 50 values following this distribution. Notice that we haven't specified the mean or the standard deviation. So we're going to take the default. In R, the default is 0 and 1, a mean of 0 and a standard deviation of 1. We'll also run this code, which is you take your x's, and to each one of them, to each of these 50, you add another randomly generated value, but this time with mean 50 and standard deviation of 0.1. And then we're going to calculate the correlation. So that means why don't we plot it, and should hopefully give us a better idea. As always, if you want to clear everything, it's like this. So we'll start with our first vector. It's going to contain 50 values. These 50 values over there. See? 49, this is the 49th entry. And as a result, this has to be the 50th entry, as you would expect. We're going to create a second vector, which is the original vector, each entry in the original vector. And we add R norm 50. I'm adding two vectors, by the way, over here. X is a vector, and I'm creating a new vector. I'm not giving it a name, but it is a new vector. We said we'll try writing a space, leaving a space after each comma. Standard deviation is equal to 0.1. Okay, so we have, yes, was there a question? Not yet. Okay, very good. Let me plot them. Let me plot them. Look, this is what we mean by they are correlated. It means, yeah, good question. How to explain correlation? It's sort of X and Y. They have the same. I'm not going to. One, I don't think I can give a very good explanation of correlation. I have an intuitive understanding of correlation, but you're measuring kind of how closely one variable follows the other variable. And if I do correlation x comma y, this is our correlation. The highest possible correlation is 1. The lowest possible correlation is -1. So with 0 meaning that they are not correlated at all. So for this session, it's just enough to know that when you're comparing two data sets, when you're comparing two variables, x and y, if the correlation is 1, they are perfectly correlated. That means if you know the value of x, you know the value of y. They are perfectly correlated. If the correlation is -1, if you know the value of x, you know the value of y, but it is a negative. It is the negative version of x. If there is 0 correlation, then there is absolutely no relationship between x and y. All the points would just be scattered everywhere. It would just, I wonder if I could do this. I wonder if I could quickly, what if I took z, oh, is it typing it over there? What if I took z and I said R norm 50. And what if I now plot x against z? See? This is what we mean by very low correlation or zero correlation that's calculated. And look, instead of being very close to 1, it's what I'm going to describe as close to 0. Not too important for what we're doing today, but it's good that we're at least using the vocabulary. By default, our norm creates standard normal random variables. This is what I was referring to earlier. If you don't specify the mean and the standard deviation, it's a very specific member of the family of normal random variables. In fact, it's referred to as the standard normal random variable with a mean of 0 and a standard deviation of 1. However, the mean and standard deviation can be altered using the mean and SD arguments as illustrated above. Sometimes we want our code to reproduce the exact same set of random numbers. We can use the setSeed function to do this. The setSeed function takes an arbitrary integer argument. For example, 1303. We use setSeed throughout the labs whenever we perform calculations involving random quantities. It's a great way for us to check that we're getting the same values as the book. In general, this should allow the user to reproduce our results. However, it should be noted that as new versions of R become available, it is possible that some small discrepancies may form between the book and the output of R. The mean and var functions can be used to compute the mean and variance of a vector of numbers. So mean is the same mean that we learned at secondary school. It's summarizing your data, whereas the variance I shall always describe as giving you an idea of the variability within the data. A zero variance would mean the data's homogeneous. Each data value has the same, each data subject, beg your pardon, each data subject, each observation has the same data value. Applying square root to the output of var will give the standard deviation. So this is just the definition. If you square root the variance, you get what we call a standard deviation. So, for instance, look at this one. Look at this one. As you would expect, if you generate 100 observations that follow the standard normal distribution, then you should expect their mean to be roughly 0. That's just the definition of the standard normal distribution. How do we know it's the standard normal distribution? How do we know that it's not just any normal distribution? Because we haven't specified the mean and the SD. This is the standard normal distribution. So think of your histogram, but instead of 180 as your mean, 0 as your mean, and your standard deviation is 1. And in fact, if you calculate the variance, of this vector, of these 100 randomly generated data values, and you square root the variance, you will get a standard deviation which is quite close to 1. It's not awfully close. I mean, it's 15% off, but it's quite close to 1. Now, what if we took 1,000 or 10,000? Then you would expect, so let's say, why don't we clear everything? RM list is equal to, yeah, cleared everything that way. And if we say new observations, and we generate 10,000, and we could say a mean of it could be negative as well. Think of maybe temperatures in a specific country. So -5 and an SD of 2. And that's your histogram. That's your histogram. And if I do mean of new observations, we get roughly -5. If you do variance of new observations, you're not going to get 2. You have to square root it. It's just the definition, the standard deviation of a data set, the standard deviation of a random variable is the square root of the variance. And what am I expecting? I'm expecting roughly 2. Yeah, close enough, right? To 2dp, that would be 2. Graphics, the plot function is the primary way to plot data in R. For instance, plot x, y produces a scatter plot, which is what we did earlier, of the numbers in x versus the numbers in y. There are many additional options that can be passed into the plot function. And if you want to see all the options, so as you type plot, although arguments to be passed to methods such as graphical parameters. That's interesting. Why do they come up like this? So L for lines, O for overplotted. So there are these options, but I'm not entirely sure why we have ... I don't know why they're not listed individually. Right. So look, we're going to generate 100 numbers following the standard normal distribution, a further 100 from the standard normal distribution. We're going to plot, and instead of just saying plot x, y, you could say x label, this is the y-axis, y label, and the main. So now, and it's inverted commas because it's text, it's a string. So let's do it very quickly. This, plot x, y, x label is, this is the x-axis, y label, this is the y-axis, and main plot of, needs to be a string, plot of y against x. And there we go. There we go. So this is a scatter plot. We will often want to save the output of an R plot. The command that we use to do this will depend on the file type that we would like to create. For instance, to create a PDF, we use the PDF function, and to create a JPEG, we use the JPEG. Interesting. The function dev_off indicates to R that we are done creating the plot. Okay, I mean, it's not that important, right? You could try it. You could try it in your own time. The function sequence can be used to create a sequence of numbers. For instance, sequence a comma b makes a vector of integers between a and b. There are many other options. For example, you could tell it from 0 to 1, evenly spaced, and 10 of them. 3:11 is a shorthand for sequence 3 to 11. So look, we could create this one. These two are relatively straightforward, I would imagine. But this is going to create a vector with 50 entries from -pi to pi, all evenly spaced. So what's the spacing going to be? I guess it's going to be 2 pi division by 50. We could check that very quickly. So my vector sequence -pi length. Was it length equals 50? Yeah. Length equals 50. Okay. And see, we have, let's just clear all this. Run it again. And now I said the spacing should be 2 pi over 50. Or maybe 2 pi over 49, actually, right? Well, let's have a look. Why don't I calculate the difference between two consecutive ones? Why don't I calculate my vector, the 30th entry, minus my vector, the 29th entry. So that's that. And what if I now divide 2 pi division by, I'm going to say 49, and it's the same number. So the vector generated over here, this is from, so 50 entries, the least entry is -pi, or an approximation to -pi, whatever R does under the hood. Greatest entry is pi. There are 50 of them, and they are equally spaced. So this would be great now to plot, for example, the cosine function, right? I could say plot my vector, comma, cosine my vector, and you get this, or I could do for sine, and you get this. We will now create some more sophisticated plots. The contour function produces a contour plot in order to represent three-dimensional data. It is like a topographical map. Are you familiar with these? If I go into my browser, I'm not sharing yet. Bear with me. What if we get like some maps in geography? Look. So the contour map is This is the contour map in pink. And it gives you a good idea. Okay, so this part is 140 meters or higher. And then this part is like between 120 and 140. Okay? Mm, it takes three arguments. A vector of the x values, the first dimension, a vector of the y values, and a matrix whose elements correspond to the z value for each pair of xy coordinates. Okay, cool. Okay, interesting. So, very interesting, very interesting. There probably isn't enough time to type each line of code, but basically what it's saying is if we can find a matrix over here, for example, this matrix, you give it this matrix, and you also tell you you need to think of it as like you're looking at a map. You're looking at a map. You're going to split the map into these four regions, and each number in the region gives you the height. So think of a column which is 1 unit high, 2 units high, 3 units high, and 4 units high. It's clear all this. So let's try and read this code. We have, what's the matrix that we're giving it? Doesn't it need 3 entries? Vector x and vector y. Are they the vector x and vector y that we had earlier? I would imagine it's this one. Now, f is this outer function. I don't know what this means. Is it going to create a matrix? Let's have a look. So let's call this x, just like the book. I'm going to say y is equal to x. Okay. So now we've created, think of it as having created a grid. Think of it as having created bird's eye view. Think of it as having created of x. We're going to exclude all these points. We're going to exclude all these points. And we're only going to work with we're only going to work with points over here. Let's do the step of pi and pi. This is kind of your x and y. Now we need a z. Now we need a z. So we're going to map each point to a, what we're going to get eventually is something like this. Your x and your y from negative pi to pi, from negative pi to pi. And we have a third variable that's a function. It's not necessarily going to be linear. It's not necessarily going to be linear, but it will be a function of x and y. Let's go back. I don't know what outer does, so this is going to be interesting. Let's see if we get it to work. I would imagine outer is going to create a matrix for the simple fact that we've just read that contour needs 3 inputs. Apparently, we're taking x, y, and f, and the f is a matrix. So let's have a look. Question mark outer. The outer product of the arrays Okay. Can't read it all. Skimming it doesn't seem to give me much information. But let's see. X comma Y. I'm sharing our studio, but I'm looking at the book as well. I'm just copying over here if you're wondering where I'm getting all this from. Okay, see, so it's created. Let's save it as F. Look. It's created this data. It's created this data. It's a 50 by 50. It's a 50 by 50 grid. Okay, so now we have our X variable, our Y variable, and our matrix. The matrix just contains all the outputs. So might have made more sense to take maybe only 10 of them. Let me show, or only 5 of them. Look. This is what we've created. Earlier it was a 50 by 50. That's what the book is using. It's creating a 5 by 5. So it's saying you have this output at negative pi comma pi at negative pi comma pi, you're going to have an output of negative 0.91. Okay? And then you move a bit, and you're filling this entire square region. Let's take it 50 again. We can finish by typing contour x comma y comma f, and look, we now have this contour map. It's giving us the heights. So you have negative heights, you have positive heights, and negative heights. I could probably show it to you in GeoGebra just to and promise this will be the very last thing we do. So look, 3D calculator, cosine y divided by cosine y divided by 1 plus x squared. Ta-da! Can you link this surface? That's a surface, right? It's non-linear, but it's a surface. Can you link these two things up? Do you see the parallels between them? What we've done with this contour function is it is a convenient way of communicating this information without drawing a 3D diagram. Ah, I think you can specify the number of levels. So right now, maybe there's a default setting. You have maybe 4 levels or 5 levels. But if we specify n levels is 45, there you go. It's more detailed. By the way, these contour diagrams, they should give you a good idea of kind of the gradient. Of course, it's not the gradient of a curve, right? Over here, it's not like at A level. And apparently, we could also do add equals t. What does add do? Add to current plot. Okay, I don't think that really changes anything in this case. So if we only take 15, oh, because it's added to the current plot. So let me delete this, and this should create a new one from the very beginning. Okay, excellent. What we'll do next session is we'll start looking at how we're going to call, how we're going to refer to specific data values. So for example, if I have a matrix 4 by 4, and notice it's by default, it's populating, it's filling the array or the array column by column. If I say A square brackets 2 comma 3, that means the second row, and the third column. But we'll do this when we next meet.